All right, this lesson is on tangent line or linear approximation here. And um, what we're going to be doing here is we're going to be doing some stuff that we've done before. We're just sort of thinking about it in a slightly different way. So here's what we want to be able to do. We want to first recognize that in some situations, a tangent line to a function may be used in an approximation for a function. We want to then be able to find what is called the linearization of a function at a given point, which is basically just the equation of the tangent to that function at that point. And we've done this kind of thing before. Then we want to use that linearization equation to find approximate values for a function, and we want to be able to use the concavity of the function to predict whether those approximate values are over or under estimates of the true values. So we want to find this linearization or this tangent line approximation and use it as an approximation in certain situations. So what is this all about here? So we've got to imagine that we've got some function f of x here, which has some curvature to it, and we can construct a tangent line to the function at a particular point. The point here is a. Now, if we take a look at this function f of x, it's got a certain curvature to it. But if we zoom in on it, on any tiny sort of like little region of it, like right in here, and we zoom in and we make it much, 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 much larger, what we would see is that in that tiny little, well, in fact, we want to actually even look at a smaller region than what I've circled there. Let's get rid of this stuff. And let's just look at a tiny little region right around in here and zoom in on it. What we would see is that our function would look kind of like this, and our tangent would look kind of like this. So even though we look at the function and the tangent, we can see that the function is curved. If we get in really, really close, like in this area right in here, we can see that the function looks pretty much linear here. So if we are very, very close to this point, A, the values that we get from the function, f of x, and the values that we get from using the equation of the tangent at that point are going to be very, very similar to each other because the curve is almost linear. So the idea behind tangent approximation here is we can take the values of f at a and f prime at a and use them to find the equation of the tangent line, and then use that equation of the tangent line to find an approximate value of f at x is if f at x is close to a. So we don't want to do this in cases where sort of our x value is way over here, because in this case you can see that there's a large difference between the value that we would get from sort of using the function and the value that we would get using the equation for the tangent. We want to do it in cases where, like if we go into the zoomed in thing, the value of our function is right here, the value that we would get from the tangent is right over in here. So we want to do it only in cases where the x value is very, very close to the value of a that we're using to construct our tangent. Now, in what cases is this, like why not just use the original function to calculate these things? Why bother using this tangent line approximation? This is often done in cases where like you want to find y equals f of x. Some cases, this can be very, very hard to compute. You've got a very, very complicated function that is computationally expensive to evaluate. But it might be easy to find the value of that function at a particular value of a. So it could be that you might already know what the function is. It could be that you know that the function values of the function are tabulated for certain values of x. So you know one of them, and you know the value of the derivative. Sorry, not at x, but at that particular point as well. So if we know the value of the derivative and the value of the function at a particular point, or they're really easy to find, and that value of a is really close to the value of x that we're interested in, then we can use our tangent line approximation. Okay, so how do we do this? Well, basically, all we're doing is we're finding the equation of the tangent to our function f at x at this point, given by a f at a. So we need our point, we need to know the slope, and let's just say that we know the slope. We know f prime at that particular point. Well, we know how to find the equation of the tangent. We just use the old y equals mx plus b. We put in our y value, which is f at a. Our slope is f prime at a. Our x value is just going to be a. So let's just say this is times a plus b. And then let's work out what our value for b is going to be. It is going to be f at a minus f prime at a times a. So our equation for our tangent is y equals f prime at a times a. Sorry, not x times a. We want to go back to the general case here, x plus our value for b here, f at a minus f prime at a times a. We can rearrange this a little bit by sort of grouping some terms together. So I'm going to pull out the f at a, and then I'm going to factor out the f prime at a, f prime at a times x minus a. So this is, we call this yt, so this is the value of y that for our, this is the equation of our tangent, and it's going to give us sort of a y value from the tangent. Value of the tangent. So this kind of thing is often called the linearization equation. The linearization of f at x at, we'll say at x equals a in this case. So because it's called the linearization equation, it's usually called, instead of f at x, L at x. So L at x is just, as we have up above, f at a plus f prime at a over x minus a. So once again, if you know the value of the function at some point, a, you also need to know this, the point that you're interested in all of this stuff in it, and you know the value of the derivative at that point, or the rate of change, or something like that. If you know these things, then you can get the linearization equation pretty easily here. Okay? So let's look at like an actual example here. Use the linearization of f at x equals 3x squared at the point 1, 3 to approximate the values of f at 0.9 and f at 1.01. And then we want to figure out if these are estimates, these are overestimates or underestimates. Okay, so we know that our linearization is f at a plus f prime at a times x minus a. So in this question, the value of a is 1. This is the x value where we're interested in finding our tangent line approximation. We can figure out what f at a is. So f at a is f at 1. We can just sub this in directly. 3, 1 squared, so that's going to be 3. So f at a is equal to 3. And in this case, because we're given the function, we can figure out what f prime at a is. F prime at a is going to be, let's see, our derivative is going to be 6x. So 6x, write this a little bit more clear, it's going to be 6x evaluated at x equals 1, because a is equal to 1 here. So that is just going to be 6. Okay? So our linearization equation is L at x equals, see, f at a is 3, f primed at a is 6, and then x minus our a value is just 1, 6 minus 1. Now, if we want to simplify this a little bit, we could do 3 plus 6x minus 6, and we could get 6x minus 3 is an equivalent expression. Now, this is so we've got our linearization. If we want approximate values for f at 0.9, we just sub in we just sub in 0.9 to our linearization equation. So our linearization is going to be 6 times 0.9 minus 3 equals 2.4. Now, is this an overestimate or an underestimate? Well, let's go back to our original function here. Our original function is 3x squared. So what do we know that this function looks like? It is, it's a parabola. It opens up. So f at x is concave up at x equals 0.9. So if the curve is concave up, we kind of sketch a little bit of that function. There's something that's concave up. We know that if we construct our tangent line is going to fall below the curve of the function, and because that's generally how it works for concave up functions. So if we are comparing, if the tangent line has to lie below the function, any approximation that we get from the linearization equation or from the equation of the tangent, that y value has to be lower than the y value that we would get from the function. So 2.4 has to be an underestimate of the true value. And I guess this question asks us also to evaluate f at 1.01. Okay, so we could do kind of the same thing again. At x equals 1.01, our linearization, again, we're just subbing this value that we want into our linearization equation. When I do this, just using my calculator, I get 3.06. Is this an overestimate or an underestimate? Well, this has got to be a underestimate as well. Because the concavity of the original function doesn't change. The argument still applies. At point 1.01, f at x is still concave up, tangent line still lies below the curve, so it's also an underestimate. Now, in this example, like we had the original function, we could find the derivative, we just subbed all the values in. This isn't sort of a typical example of the kind of question that you're going to see. You're more likely to see something that looks kind of like this, where you're not given the original function here. So we are given that f at 3 is equal to 4, f primed at 3 is equal to -2, and f double primed at 3 is equal to -4. And we want to find an approximate value for f at 3.1. So we don't know the original function. We're just given the value of the function, the value of the derivative, the value of the second derivative at this particular point, close to the point that we are interested in. So, and then we want to figure out if it's an overestimate or an underestimate. So easiest thing to do here, let's come up with our linearization equation for our original function. So we don't know the function, but our linearization at x equals 3 is going to be f at 3 plus f primed at 3 times x minus 3, just using that equation that we developed earlier. Now, what are we given here? We're told that f at 3 is equal to 4. We're told that f primed at 3 is equal to -2. So we can just put in, just keep x minus 3, and expand this out a little bit. This is going to be minus 2x plus 6. So our linearization is going to be 10 minus 2x. Now, if what we want to find is f at 3.1, we can evaluate this at 3.1. Punching this into our calculator, what we're going to get here is 3.8. So our approximate value for f at 3.1 is this 3.8 that we get from the linearization equation. Now, is this an overestimate or an underestimate? Well, at x equals 3, f double primed at x is -4. So f double primed of x is less than 0. So if our second derivative is less than 0, our curve is concave down. If our curve is concave down, then our tangent line is going to lie above the curve of our function. So our linearization is going to be an overestimate. So we can say tangent line is above f at x. Therefore, it's going to be an overestimate of the true value. All right, one last little example here. Estimate the square root of 27. Okay. So it's phrased considerably differently than the previous questions were, but we can still think of this using a tangent line approximation. So we can think of this number that we're given here. Like, we're trying to find the square root of 27. We can think of this as the square root as being a function. A function being f at x equals the square root of x, or x to the 1/2. Where do we want to evaluate this thing? Well, we want to evaluate this at x equals 27, but we can think of this 27 as being made up of 25 plus 2. Now, we know what the value of f at x is at 25. Okay, we know that the square root of 25 is just 5. So we can use a equals 25 as sort of our reference point where we're going to find the slope of the tangent. Okay, so our linearization equation, L at x equals obviously f at a plus f primed at a times x minus a. So if a is 25, f at a is going to be the square root of 25. F primed at a, well, let's see, f primed is going to be 1/2 7 to 25 there to the -1/2. I'm just taking the derivative, subbing in the value of a. And the x value that we're interested in is 27, and our a value is 25. So let's evaluate this. The square root of 25 is 5. Here we've got 1 over 2 times, this is going to be 5. 1 over the square root of 5. 1 over the root of 25. And then 27 minus 25 is going to be 2. So 2 and the 2 are going to cancel out, and we're going to be left with 5 plus 1 over 5, which is like 5 and a fifth, or when it is a decimal, it's going to be 5.2. So if we go ahead and we actually calculate the square root of 27, what we get is 5.196. So we got a reasonably good estimate here, accurate to, rounding this off to one decimal place, these two are exactly the same, just because we knew what the function, the value of the function was at a, where it's at 25, where it's easy to calculate, and applying that knowledge in our linearization equation. So I was going to do another example here, the cube root of 63, but I'll kind of leave that one because it's very similar to the one that we just did here.